Today I introduce our final project from Gigapixel pathology images. The traditional procedure of diagnosing breast cancer contains 4 steps: biopsy, preparation, visual inspection, and diagnosis, followed by treatment plan. A pathologist comes to play at the step of visual inspection, where they use microscopes to inspect on a ton of slides, which could be tedious and as a result time-consuming and error-prone. Now, with computer-assisted diagnosis, it should effectively reduce the rate of misdiagnosis, increase in sensitivity, speed, consistency, and also at a minimal cost with enough data. The dataset we used for the project comes from Chameleon 16 Challenge, in which there are images of type WSI known as whole slide images, and there is 8 levels of magnification in each of them, as shown on the right. So with the different zoom level provides context and details to our model, which should enhance its performance of prediction. Also, there is slide level annotation, meaning there is, for each image at each level, there is a mask indicating which pixels are marked as tumors for ground truth. The theoretical foundation of our project approach is based on this paper, Detecting Cancer Metastasis on Gigapixel Pathology Images by Liu Ying et al. Also, we did our data pre-processing using OpenSlide, which is an open source C library for processing whole slide images. In the next steps, we've also done color normalization as well as feature extraction. Here is an example of the same part of tumorous tissue shown on different zoom levels. We have picked our training slides to be the 16th, 101th, 84th, 94th, and 96th. For each of these slides, we extract patches from level 5 and 6, and in total we have collected 120 positive patches and 170 negative patches. Positive patches means that in this patch there appears tumorous tissue, whereas in the negative patches there's only healthy tissues. Here are 2 examples of the training slides we picked. So here is a demonstration of how the mask actually works with the original image. On the bottom left, this image is the original slide image, and the second image shown is the corresponding mask, where the yellow regions actually indicate the pixels on which there should be marked as tumorous. And on the bottom right image is an overlay, which is simply a projection of the mask on top of the original image. In our approach, we choose to extract patches of size 299 by 299 from the original image of shape 1,000,000 by 1,000,000. Therefore, there are a lot of regions that there is no tissue. Therefore, we choose to set a threshold of above 50% of pixels to be tissue, and among those, we create 128 by 128 center regions on each patch, and check if there exists any tumorous tissues. If so, we add the patch to positive samples. Otherwise, we add it to negative samples. And one caveat we've done is that we actually collected positive samples from masks due to the small proportion of tumorous tissues to speed up the entire process. We also picked our testing slide to be the 110th slide, as shown here. More examples of patches. So at level 7, of slide 101, we have the original slide shown here on the left at level 7, and in the middle there is the overlay, and on the right it only shows the tissue part of the slide with a tissue ratio of 0.79. So the way we incorporated transfer learning to our model is that we trained two models based on two different convolutional bases. We chose to use VGG16 as well and Inception v3, and on top of both, we've added two dense layers. And also we trained both models on Colab. On the top right is the architecture of VGG16, and on the top bottom is the architecture of Inception v3, and together with our top levels, it should give a big picture of the pipeline of our model. We've also created heat maps for each experiments we've done, and the one method we use to generate heat maps is the sliding window, where we choose patches of size, where we generate patches of size 299 by 299 from the test slide and do the prediction on zoom level. However, the heat map is produced on the reference level, which is default to 7. For each heat map, we've also included confusion matrix-based evaluation metrics, namely accuracy, F1 score, recall, and precision. As it is shown here, the matrix on the right is plotted for ground truth against prediction, where there could be truth positive, truth negative, false negative, and false positive. Since our project that concerns breast cancer detection is a class imbalance problem, accuracy is not very useful measure. Therefore, we focus on recall, precision, and F1 score. Recall is the correct prediction given the true positives, true positive plus the false negatives, meaning the cells that actually contains tumors. And precision is the correct predictions given all the predictions that we claim to be positive. F1 score is the harmonic average of recall and precision, and its max value could be as high as 1, and its worst could be 0. So here are some examples of the heat map as well as the evaluation metrics calculated on some experiments we've run on our test slide. So this is Inception v3 based on level 5, and as we can see here, it shows pretty good, pretty accurate predictions compared to the reference. Also, it has an F1 score of 0.87, which is pretty close to, which is pretty high. So this one is the VGG16 model based at level 5 that has F1 score of 0.88. And lastly, the VGG16 based at level 6, which has relatively lower F1 score, however, with a pretty high precision of 0.90. We've also plotted the evaluation metrics for each experiment to a bar chart. As we can see here, the Inception v3 model at level 6 has the highest F1 score, as well, and it is also the most successful one relative to when measuring precision. But we've seen VGG16 at level 5 to have the highest recall. So in conclusion, both the models works pretty good. As we can see, the VGG model has scored a AUC measure 0.99, and same case for the exception V3 model. And the potential, I guess, the potential improvements we could have done is to train with more data and extract data from more levels. We might also include image augmentation. However, these all actually makes the training data a lot bigger than the data set we have. So as a result, we might need more calculation power, which we might have if we were to run the model on Google Cloud Platform. However, due to time limit, we'll only train our model on Colab. Thank you very much, and if you're interested, please visit this URL for more information and source code. Thank you.